Hello, this is Millie Warner, and I will be presenting my Lab 4 report on oscillations of springs. Please excuse my voice, I have a cold and my throat is a little scratchy as a result. The goals of this lab are to observe the motion of an object attached to a spring oscillating back and forth, use Tracker to gather data about the position of the mass as it oscillates, create a computational model measuring the change in energy of the mass spring system, compare the predicted motion with the actual motion in the x and y directions, and consider the energy principle as well as the different estimates for the period of oscillations. Let's discuss some of the fundamental principles needed to explain the phenomena in this particular lab. We will use Newton's second law of motion to update the velocity every time we iterate through the code. The law is as follows. Velocity final is equal to velocity initial plus F net divided by the mass times the change in time. Next, we will utilize Hooke's law, or negative k times the length of the spring that has stretched, in order to determine the spring force. On the other hand, we need to also look at some formulas regarding energy. The general energy principle states that the total change in energy is equal to the sum of the changes in individual types of energy. For us, the total change in energy consists of the change in kinetic energy, plus the change in gravitational potential energy, plus the change in the spring potential energy. More specifically, the change in kinetic energy is equal to 1/2 the mass times the square of velocity. Gravitational potential energy equals the product of the mass, the gravitational constant, and the vertical distance from the Earth. Lastly, spring potential energy is equal to 1/2 the spring constant times the square of the stretched spring distance. Here is a screen recording of my tracker trial. You can see that I use 0.7 meters for my calibration stick, and I set the origin as the base of the spring. I tracked the motion through multiple oscillations, and as you can see, my position data on the right for both the x and y directions. Notice how the position graphs produce wave-like data. This makes sense for our oscillations as these waves provide information about the period and frequency of the movement. Next, we need to recognize and find some information about the motion to enter into our glow script code. The mass of the object is 0.402 kilograms. And the initial position values were found by simply looking at the data in Tracker. I set the initial velocity to 0 meters per second, as we are assuming that the mass is starting from rest. To find the period, I took the average of 3 oscillations. Using this method, I determined the period to roughly be 1.6143 seconds. I found the spring constant next, which ended up being about 6.089 newtons per meter, using the given formula. Lastly, I calculated the relaxed length of the spring by subtracting the mass times the gravitational constant divided by the spring constant from the length of the spring with the mass. This value ended up being 0.053 meters. Now I will point out some of the changes I made to my code. Firstly, I entered in the necessary known and calculated values for mass, initial position, initial velocity, spring constant, and relaxed length of the spring where applicable. Next, I described the length and orientation of the spring using L, L hat, and L naught. After this, I formulated the different types of energy. In this lab, we only concern kinetic, gravitational potential, spring potential, and total energies. Then I calculated the net force of the mass from the gravitational and spring forces. In the while loop, I updated the position vector, the velocity vector, and the spring data in order to progress through the motion. Lastly, I calculated the changes in all types of energy, and I added these changes to get the total change in energy. Now I will run my code. As you can see, the motion from the predicted data and the motion from the observed counterpart are quite similar. Some sources for discrepancies range from human error while operating Tracker and other forces, such as the drag force, that are unaccounted for in the code. Is the energy principle satisfied in the system? The computational model would suggest that yes, it is. As you can clearly see, the orange line, which represents the change in total energy, remains roughly 0 for the entire duration of the code. Because there is no change in total energy, albeit changes in kinetic, gravitational potential, and spring potential energies, the energy principle is satisfied. The last task for this lab is to estimate the period of oscillation from the x position data as well as the y position data. By clicking on certain points of data in Tracker where the mask completed one oscillation, I found that the period in the x direction is 1.614 seconds, and the period in the y direction is 1.519 seconds. These values are extremely close but different yet. These discrepancies, like I mentioned before, could have resulted from error in choosing the center of mass for each frame in Tracker, the nonlinear path of the spring, and the unaccounted forces. Thank you for watching my presentation, and have a wonderful day.